if that ratio happens to be exactly 1, then the test is conclusive. What would the comparative test be?
That have sequences less than a sequence that converges, and it converges, and it's greater than a sequence that diverges.
Term by term.
Term.
So every term has to be smaller than the corresponding terms of a convergent sequence. Then the sequence that you are looking at is also convergent. If term by term, the sequence that you are looking at is bigger than a series that you know diverges, and the series that you are looking at diverges. Now, sometimes you cannot use the comparison test straightforward. If you had something like this, what would you like to compare this with? Well, you can compare it with 1 over k squared, or k squared plus 1. Well, let's take a look at the two terms. What's the first one? Oh, 2. Now you can compare it with this. Why not? By the way, what do we know about this view? Convergent or divergent?
That's conversion.
Yeah, it's K. It's a P series with K, and this is even bigger than 1 over 1 squared. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. That converges because that's a P series. K, the P equal to 2. And these are even small. How can you compare these? What would be the logic? No logic. What can we say? Well, we know this converges. Small numbers. What can we say about this? Nothing. Because these are bigger than these. So what? So we can't use the comparison test there. Now, anybody know whether the series converges or diverges? Who thinks it converges? Who thinks it diverges? Who doesn't know? Mr. Matthew, why do you think it diverges?
Intuition.
What is your intuition telling you?
That it's not big enough on the bottom. It's not fast enough on the bottom.
Why is it not fast enough?
Because it's only 1 degree greater.
Correct. What is going on here? If you look at, let's say you go to 6. You keep going, you can go 100 over 100 squared plus 1 plus 1,000 squared. And 1,000 over 1,000 squared. Now what does this look like? It may look like 1 over 1,000. The next one, like 1 over 1,001. The one after that, 1 over 1,002. What series is that?
That's one of our square ones.
Huh?
1/k.
The harmonic series, which we know diverges. So your intuition is that eventually this starts to look like 1/k. Eventually. If you take your jacket off and you say, well, what is the sequence? In the limit, the sequence is 1/k. So it's approximately in the limit, that is a large K. Which we know diverges. What you say, well, compare the series with 1/k, series for 1/k. That is to say, eventually, the terms of this sequence start to look like the terms of this sequence. So eventually, the series starts to look the same. This is called the limit comparison test. The limit comparison test. Okay, let us assume that our series are non-negative. Let us assume the sequences are non-negative. There's not a big deal about making them negative. Let us suppose that when you take the ratio of these terms from the sequences, say what happens to this sequence when n is big? What happens to this sequence when n is big? Are they approximately the same? Find that ratio. Now this is not the ratio test. In the ratio test, you compare the next one with the previous one from the same sequence. Huh? The ratio test is this. You want to know it doesn't start to behave like a geometric sequence. That ratio. It's not finite number. But here you are looking at two sequences, and you are looking at eventually how did the two sequences compare term by term? Eventually. Eventually, how do the two sequences compare? Now that number L could be 0, it could be 3/4, it could be 5, it could be 2/3, it could be 20, or it could be infinity. That is to say, this one grows much faster than this one eventually. But let us suppose, this is the hypothesis, and you will have to show it. L is strictly less than infinity and strictly greater than 0. So that number is like 2/3 or 3/4 or 10. If that number is 0, then you really can't compare. You can't compare. This one converges with this one. And if that number is infinity, then you can't say anything about two sequences. But If this number is a finite number bigger than 0, the two series are the same as far as convergence goes. That is to say, either both series converge or both series diverge. Suppose that this limit is strictly positive and strictly finite. Suppose then either both series converge or both series diverge. That is to say, they are the same as far as convergence goes. So let us take a look at this one here again. Now, Mr. Collas, you're correct that you have an intuition this is divergent. What would be one way to prove that this is divergent? Integral test, right? You integrate x over x squared plus 1 with a natural logarithm. You have infinity from 1 to infinity. However, since you have an intuition there, it starts to behave like what's equal. So we're going to do a little from that.